Welcome to week 5. In this week we will be discussing about the ways to characterize polymers. We will also conclude by looking at the design aspects for polymers. But in this video we will focus on this dynamic mechanical analysis. This is a very common technique to characterize the dynamic properties of the polymers. So, dynamic mechanical analysis is commonly called as DMA, the acronym for it. So, what is done in this experiment is we find the response to steady state oscillations. So, when we vibrate or oscillate a sample, we look into if the input is stress, we measure the strain, and if the input is strain, we measure the stresses. But these experiments can be done in different configuration, including tension, compression and bending. But for the sake of simplicity, let us focus on tension for this video, but the same can be extended to compression as well as bending. Let us see what are the inputs we can give while doing this test and the typical responses we observe. So, first let us talk about stress input. Let us say sigma of t is given as sigma naught times cos omega t. Let us try to represent it using a plot. So, for the x axis we will take it as omega t. Omega here is a frequency and t is the time. So, since we are talking about cos, at 0 it starts with a maximum value and then goes to negative and then repeats. Okay. Now, let us see what is the response to this load. So, the output will be strain, and once we look at strain, since we are talking about cyclic loads, so when the input is cyclic, the output is also cyclic, and usually when it reaches the steady state, both are in the same frequency. So, it will be sigma naught times cos omega t minus delta. Let me explain you what is this delta. Delta is the phase lag. This we can represent in the figure. So, what we are now saying is both will have the same frequency, both the input stress and the output strain, but the difference is the output strain will be lagging behind with the input. So, which means instead of reaching the peak at time t equal to 0, it will reach at another time instant. So, the one in the red is the strain output and one in the black is the stress input. So, we see that both of them have the same frequency, which means the wavelength is the same, but the peaks or the times at which they reach 0 are different, and that difference is represented by this is the delta or the phase lag. So, essentially what we are saying is the input and the output will have the same frequency, the only difference is the output will have a change of phase which is represented by this delta in the plot. But I have here shown you only one of the many possibilities. So, there is another possibility we can write for the stress input, which can be written as sigma naught times sine omega t, meaning at time t equal to 0 the input is 0 and it keeps increasing and reaches the maximum value and comes back to negative and then back to 0. But instead of the stress input we could also have seen the strain input. So, let us say epsilon of t is simply given as epsilon naught cos omega t. So, the output we can see it as output stress sigma of t is epsilon naught times cos omega t plus delta. So, here too again we are saying that there is a shift and that shift is delta. To be consistent we are writing it as plus delta, meaning that instead of lagging it is ahead. And the other possibility of the strain input is we can write it as epsilon naught times sine omega t. So, the way to approach this problem or to solve this problem is to use complex numbers. So, that is what we will show. Taking one of these inputs, we will see how complex numbers or the complex analysis can be applied to solve these problems in a much more simplified fashion. So, just a quick review. We know what is a complex number. I is square root of minus 1 and the Euler formula e power I theta is given as cos theta plus I sin theta. The reason why we are looking at this is now we will see there is a more uniform way to look at the inputs. So, for example, let us say if I write it as e power I omega t, then it can be written as cos omega t plus I sin omega t. So, let us say if I multiply, so looking at the strain input, let us say here epsilon of t, right. I could simply say epsilon of t is epsilon naught times e power I omega t, then it will be epsilon naught times cos omega t plus I times epsilon naught sin omega t. So, now this final expression has a real term and a imaginary term. So, the first one is the real term, real part, and the second one is the imaginary part. So, the reason why we are emphasizing this is the real part becomes the input shown here, and the imaginary part is the second input shown here as epsilon naught sin omega t. So, if I am able to write it in this format, essentially I am taking care of both the inputs, both the cosine input as well as the sine input. So, what I will show in the next slide is how to solve this for a generalized in terms of the complex analysis, for which means in one go we will be solving both the problems for both inputs, cos input as well as the sine input. So, as seen previously, we are saying that the strain input is written in terms of complex numbers, so that it will take care of both the cos as well as the sine. So, if I expand this, it is simply but let us avoid going into this cos and sine right now, we will work with the complex e power I omega t. So, now let us look at the output. In terms of stress, we will write it as sigma star, where sigma star is a complex stress times e power I omega t. The reason why I am able to write it as e power I omega t is from our observation that the output also has the same frequency. Okay. Now, what we will do is we will replace this sigma star So, now we will replace this sigma star as E star times epsilon naught. What is E star here? E star we will define it as the complex modulus. Okay. So, once we substitute this, it will be E star times epsilon naught e power I omega t. So, if you look carefully in this second equation we wrote, the right hand term is simply what? E star times the strain input epsilon of t, right. So, this is one way to look at the Hooke's law, saying that the stress and strain is related with this complex modulus. Okay. But again this complex modulus can be written as real and imaginary terms. So, we will write it as E dash plus I E double dash, where E dash is the storage modulus and E double dash is the loss modulus. So, the reason why E dash and E double dash have these names of storage and loss modulus is because the first term, the E dash, takes care of the stored energy per unit cycle, and the E double dash you will see is proportional to the energy dissipated. Because we are talking about viscoelastic, which means viscous means there is dissipation, the amount of energy dissipated is captured through E double dash. So, let us say if D is the energy dissipated, this is given as epsilon naught So, here we see that the dissipated energy D is directly proportional to only the loss modulus and not the storage modulus. So, that is why there is a significance into writing this complex modulus in terms of this storage and loss modulus, because it gives a sense about E dash storage modulus is a sense about the elastic behavior of the material, and E double dash, which is the loss modulus, it gives us what is the viscous behavior of the material. Okay. So, now let us substitute this formula into this expression of output stress. So, it will be E star E dash plus I E double dash times epsilon naught e power I omega t. Okay. So, what we have achieved is we are able to write the output stress in terms of these new quantities, the complex modulus, storage modulus and the loss modulus times the input strain. In the next slide, now we will go into these specific loads, the cost load and the sine load. So, we will start with the cost load. So, here we said the strain input epsilon of t is epsilon naught times the cos omega t. So, from our previous discussions we know this is the real part of epsilon naught times e power I omega t. Now, to find the output stress, we simply need to look at the real part of complex modulus E star times the strain. Strain is epsilon naught times e power I omega t. So, now let us find the real part of this expression and then we should be able to find the stress. So, let us expand it out. I will replace the complex modulus with the storage and loss modulus, and we will also expand this e power I omega t in cos and sine terms. It is cos omega t plus I sine omega t. So, once I multiply it, epsilon naught will be a constant, E dash times cos omega t minus, because there is I times I square is minus 1. So, we get this minus times E double dash sine omega t. This will be the real term, and if we write the imaginary term, it will be I epsilon naught times I times. So, E double dash cos omega t plus E dash sin omega t. Since we are only interested in the real part, it is simply epsilon naught times E dash cos omega t minus epsilon naught E double dash sin omega t. This will be our output for the input of epsilon naught times cos omega t. But having found this, now let us see how do we bring in the phase lag or the delta. For that, if you look closely, this can be written as an expression of cos A plus B, where we know it as cos A cos B minus sin A sin B. So, the way we write it is so if I multiply and divide by sigma naught, this I can write it in terms of cos A cos B formula, which is simply sigma naught times cos omega t plus delta. But now let us see what is E dash in terms of delta. So, according to this expression, we should be able to write this E dash is sigma naught by epsilon naught times cos delta. And what is E double dash? Again sigma naught by epsilon naught times sin delta. Now, we can see that we should be able to write this tan delta, which is simply the ratio of the loss modulus by the storage modulus. So, in the literature of these polymers, tan delta is very commonly used, because tan delta is one of the ways to find the glass transition temperature. That we will discuss more in the next class, but let us identify that delta is an important quantity, and that is why we are looking at here. Okay. So, what we are able to show is for this given input, the output is written in terms of sigma naught times cos omega t plus delta. So, as we can see, both have the same frequency, the only difference is there is a phase shift given by this delta. And more importantly, on this slide we have defined what is the storage modulus given in terms of delta and sigma naught epsilon naught. Similarly, the loss modulus is also given by this sine delta, and tan delta is simply the ratio of the loss modulus to storage modulus. So, once we have solved this, one should be able to also solve for this input sine input. So, epsilon naught times sine omega t. By looking at these, instead of looking at the real part, now we will be looking at the imaginary part. So, even in the output, if we only look at the imaginary part, we should be able to write it as sigma of t is this imaginary part given as epsilon naught cos omega t e double dash plus okay. In the next slide we will see if the input is stress, how do we solve it? Using the same approach, it is just an exercise. So, here we see that the stress input is given in terms of again sigma naught times e power I omega t, and as we have seen e power I omega t will take care of both the cos function and the sine function. So, if we are looking for the output, again like previously we will simply start with some complex strain epsilon times e power I omega t, saying that we are able to write this because we observe that both the input and the output are having the same frequency. Okay. Now, if I am able to write this complex strain as so, here I am able to write this complex strain as d star, which is the complex compliance times sigma naught, and once we substitute this into this expression, it will be d star times sigma naught e power I omega t. So, we will also rewrite this complex compliance again in terms of the storage and the loss terms. This time we have the storage compliance and the loss compliance. So, d dash plus I d double dash, where d dash is the storage compliance and d double dash is the loss compliance. So, once we substitute it back, so first we will look that this can be written as d star times the input stress, because once we look at this sigma naught times e power I omega t, it looks like the input stress sigma of t. But again if I substitute this in terms of the storage and loss compliance, epsilon of t is written as sigma naught d dash plus I d double dash times e power I omega t. Okay. So, now we are able to introduce this complex compliance, storage and the loss compliance. This happens when our input is the stress, but previous slides we have seen if the input is the strain, we discuss about the complex modulus, storage and the loss modulus. So, this should give you an overview of how to deal with different inputs, and we are using this complex analysis to find the solutions for these oscillation loads. So, now let us summarize what we have seen in this video. We said for a strain input, we can write it in a common fashion of using this complex number, then it takes care of both the cos and sines. For this input, the output is written as E star, we said is the complex modulus times the strain input. We also mentioned that this complex modulus is written in terms of the storage modulus and the loss modulus. Similarly, for the stress input, we said the output is written in terms of complex compliance times the input stress, and this complex compliance we have written in terms of storage and loss compliance. Okay. So, we also looked for a strain input, let us say epsilon of t is epsilon naught times cos omega t. For this input we have showed that the output is So, there is one very good observation one has to make when we look at this expression for output, because we see though the input is a cos term, we have both the cos term and the sine term in the output. What it means is the first term which is in the cos term is in phase with the input, which means both reach the maximum and the 0 at the same times. But the second term is completely out of phase from the first term. So, because we know that the cos and sine are two perpendicular functions, so we can say that the second term is out of phase. So, this we would say as in phase, and the second term is out of phase. So, we can see that the storage modulus E dash is responsible for the in phase component of the response, and the loss modulus E double dash takes care of the out of phase component of the response. So, the way we plot it is, let us say the input is the cos function, epsilon naught times cos omega t. Now, let us see the in phase and the out of phase how they look like. Let us change the color to blue. So, the in phase component will be in phase, meaning the maximum and minimum will match. This will be our the first component, which is epsilon naught times E dash cos omega t, and then we have the out of phase component. Let us pick another color. So, this will be the second component, which is epsilon naught times E double dash sine omega t. So, these amplitudes are given as, so for the red the amplitude is simply epsilon naught times E double dash. For the in phase component, this is epsilon naught times E dash. and for the input the magnitude is simply epsilon naught. So, just a final statement saying that there is a in phase component and an out of phase component in the response. The in phase component is coming from the storage modulus or the storage compliance, and the out of phase is coming from the loss modulus or the loss compliance. So, in the next class we will solve some problems and see how we can bring in the mechanical model to find the response for these dynamic loads.